In this section, we'll use a combination of the lecture notes as well as some handwritten examples in order to talk about the material. I was able to provide lecture notes to remind you of some of the key topics, but some of the ones that I go over by hand won't be on the lecture notes. It's a good idea to take notes as we go, because some things are just better to explain on a piece of paper or a chalkboard than they are on a PowerPoint slide, and that's going to be the case throughout the course. In fact, in some cases, it's almost impossible to explain it by a PowerPoint slide, like in stoichiometry, for example. So I may give an example that's found in the book, but I'm probably going to explain a different example. So that's just something that's going to happen in this course. Anyway, let's look at the subatomic particles. We have the proton, P+, which has a mass of 1 AMU, a charge of +1, and is found in the nucleus. We have a neutron, which is neutral, a mass of 1 AMU, no charge, found in the nucleus, and an electron, with a mass of approximately 0, a charge of -1, and is found outside the nucleus. It's very important that you know these things. Said another way, you should copy this down. The first thing to remember, or to know, is that protons define the element and are the atomic number. And protons cannot change. So in a chemical reaction, the number of protons never changes. Said another way, the element never changes. So if you look at a periodic table, and this is a snippet of a periodic table, I cut off the lanthanides and the actinides so I could make it as big as possible. If we look at hydrogen, it has atomic number 1. The number up here is the atomic number, and it's atomic number 1. That means it has 1 proton in its nucleus. And if we look at helium, helium is atomic number 2. Helium has 2 protons in its nucleus. Lithium has 3, beryllium has 4, boron has 5, and you'll notice this counts all the way up to somewhere around 109 here. Note that I took out the lanthanides and the actinides, which gets you from 58 to 71 and 90 to 103. They pop out here, but we get up to about 109. Notice that every time we have 1 more proton in the nucleus. Hydrogen has 1, helium has 2, lithium has 3, beryllium has 4, boron has 5, so on and so forth. And this never changes, and it defines the atom. So helium, the gas they put in balloons to make them float because it's less dense than air, is something with 2 protons in its nucleus. All helium atoms have 2 protons in their nucleus, and anything with 2 protons in its nucleus behaves like helium, a gas that's very unreactive and less dense than air, so it causes a balloon to float. And this is true of every element. So the protons define the atoms. The next thing we want to look at is, well, how do we know about these other subatomic particles? Protons are straightforward because they define the atom. So if something's called helium, it has 2. If it's called neon, it has 10. What about neutrons and electrons? What happens with those? Well, what we can use is these symbols of elements, and they'll tell us several pieces of information. First, they'll tell us the atomic number. In this case, oxygen's atomic number is 8, which of course means that it has 8 protons in its nucleus, and the mass number, which is on the top. Remember that there's only 2 subatomic particles with mass, the protons and the neutrons. So if we subtract the mass number minus the atomic number, or the number of protons, we can find the number of neutrons. And then in the upper right hand corner, we find the charge. If nothing is written, there is no charge. So in this case, for this oxygen, it would have the same number of electrons, each with a negative charge, as it has protons. So if something has 8 protons and it's neutral, it must have 8 electrons. Let's look at this other example. In this case, it has a -2 charge. Well, electrons are negatively charged. So in order for oxygen to have a -2 charge, it must have 2 additional electrons. Said another way, this oxygen has 10. It has 8 protons and 10 electrons because it has 2 extra negative charges. So these are essentially the symbols of elements. This is extremely important. So I would like to go over several examples, which I will do now. So here we have a few examples. So first, I'm going to put hydrogen 1, 1. Remember that this is the atomic number and usually isn't written because chemists assume that if we call something hydrogen, it has one proton. In fact, that's how we know it's hydrogen, because it has one proton. And this, as you'll recall, is the mass number. Now, something you may be asked is, how many protons, neutrons, and electrons does this have? And I should point out, I forgot because it's not here, but here, where there's nothing, is the charge. Remember that if there's nothing, there's no charge, which makes sense. Or said another way, it's neutral, or said another way, the charge is 0. So this is the symbol for hydrogen. And what you might be asked on the homework or on an exam is, how many protons, how many neutrons, and how many electrons are in this atom? So the protons is easy. If it's hydrogen, we are given the atomic number, but we would just find it on a periodic table, and we'd look at the atomic number, and we'd say it's 1. So that tells us there's 1 proton in the nucleus, and that's what makes this behave like hydrogen. To find the neutrons, we take the mass number and we subtract the atomic number. And this is always the case because protons and neutrons have mass. So the total mass is going to be the number of protons plus the number of neutrons. Said another way, if you want to find the number of neutrons, you take the mass number and you subtract the atomic number. In this case, it's 1 minus 1, which equals 0. So this hydrogen has no neutrons. Electrons. If it's neutral, the electrons and protons are equal. So in this case, we have 1 electron, which is exactly the same as the number of protons because it's neutral. Note that if it is not neutral, this is not true. Let's look at another example. Let's look at helium. Helium has, and for this helium, has an atomic number of 2, always, because it has to have 2 protons to be called helium, and this helium has a mass number of 4. In a few minutes, we'll talk about isotopes, which are examples of atoms with different mass numbers. So here we have helium like this, and we might want to know the protons, the neutrons, and the electrons. The protons is easy. You could either use this 2, which often won't be given, but in this case it was, or just look it up on the periodic table and find that this is atomic number 2. So anything called helium has 2 protons. Neutrons, in this case we take 4, the mass number, minus 2, the atomic number, because again, protons and neutrons are the only thing with mass, and we find that it has 2 neutrons. This helium is neutral, has no charge, there's no charge shown, so therefore it has the same number of electrons as it has protons, which is again 2. Let's look at one more example. Let's say we're given bromine 79, and we're asked for the protons, the neutrons, and the electrons of bromine 79. Now notice here I did not give you the atomic number, but in any chemistry exam or while you're doing your homework, of course you have access to a periodic table. So it is not uncommon for chemists to not write the atomic number down here because we called it bromine, which tells us how many protons it has in its nucleus. You're going to want to go to group 7A on the periodic table. You'll find bromine, and you look above it, and you find the atomic number. The atomic number of bromine is 35. There's something worth pointing out here. For whatever reason, on a periodic table, the atomic number is written above the atom. However, in these symbols, the atomic number is on the bottom for whatever reason. Just something to note. Now we want to find the number of neutrons. Well, to do that, we take the mass number and we subtract the atomic number. So in this case, we take the 79. We subtract 35, and we find that this bromine has 44 neutrons. Finally, we want to find the number of electrons. Well, this bromine is neutral. How do I know? There's nothing written for the charge. So that means the number of positive charges, 35, must be having the exact same number of negative charges to be neutral. So therefore, we have 35 negative charges as well. So this is how we could find the subatomic particles in atoms. Now I want to shift gears slightly and talk about subatomic particles in ions. So let's look at this example. Let's take Cl35 with a minus charge. So we have chlorine 35 with a minus charge. And again, we want to know protons, neutrons, and electrons in this thing. And now it has a charge. So let's first find the number of protons. Remember, we don't have to put the atomic number here. So if we look at chlorine on the periodic table, it's again in group 7a. It's right here. And it has 17 protons. So we look it up and we find that it has 17 protons. To find the mass number, we take 35, to find the number of neutrons, we take the mass number 35. We subtract the 17 protons, and we find that it has 18 neutrons. Now this is actually called chloride, and chloride has a charge, a negative charge, which means that it has an extra electron. So if it has 17 protons and a negative charge, it must have 18 electrons. Let's do one more example of an ion. Let's look at Fe. Fe with a mass number of 55 and a 3+ charge. So when we look at Fe, 55 3+, and we want to figure out the number of protons, the number of neutrons, and the number of electrons, we can do that. First, we have to find iron on the periodic table. And on this periodic table, on every periodic table, I don't know why I said that, iron is number 26. So that means something with 26 protons in its nucleus we call iron, and it behaves like iron. It holds up bridges and buildings and things like this in steel. So protons is 26. Now we want to find the number of neutrons. We take the mass number, 55 minus 26, and when we do that subtraction, we find out that there are 29 neutrons. Finally, we want to find the electrons, and because this this iron has a 3+ charge, it must have 3 more protons than it has electrons. So that means that it must have 26 minus 3, or 23 electrons. So when you form a negative ion, you have an extra electron. When you form a positive ion, you have 3 less electrons. Notice the number of protons can't change. Ions have the same number of protons as atoms. Anything that behaves like iron has 26 protons in its nucleus, and that can never change in a chemical reaction. Once you have iron, it's always iron. However, the charges in chemical reactions can change and sometimes do change, and we'll study some of those reactions. So what's really changing here is the number of electrons. What you'll look at later on is, well, if iron is 3+ and it gives up its electrons, maybe it could give those electrons up to chloride. And that's later in the chapter. And this transfer of electrons is chemistry, which is the study of change. But the protons don't change. What really changes is the electrons. So one can argue that chemistry is really the study of how electrons interact with each other in atoms. Now that we've looked at several examples where we found the subatomic particles, and again, there are lecture notes to remind you about these things, I do want to switch gears and I want to talk about something called isotopes. So the last thing that we're going to talk about in this section is something called isotopes. And in isotopes, we essentially have the same atom, the same number of protons, but with different mass numbers. And a classic example of this is chlorine. So if we look at chlorine, which has an isotope 35 with a mass number 35, and it also has a naturally occurring isotope with 37. So there are 2 different chlorines that exist in nature on this planet, chlorine 35 and chlorine 37, and both are stable. And if you took some sample of chlorine gas, you would find a ratio of these. I believe it's somewhere around 2/3 this one and around 1/3 this one. So that, 3/4 this one and 1/4 this one. And we'll talk about that in a minute. So let's look at this in terms of the number of protons, neutrons, and electrons for both. In this case, the number of protons is the same because they're both chlorine. So, if we look at our periodic table, we already did this one, but we can look at it again. We find chlorine, it's number 17. So, these both have 17 protons, which makes them chlorine. However, they have a different number of neutrons. This one has 35 minus 17, or 18 neutrons. This one has 37 minus 17, or 20 neutrons. Number of electrons, they're both neutral, so they both have an equal number of protons and electrons. Said another way, they both have 17 electrons. So these two isotopes, which both exist in nature, differ in the number of neutrons. So there's two ways of looking at isotopes. They're the same element, and I'm going to say with a different mass number. And of course, what gives them a different mass number is a different number of neutrons. That's what gives them a different mass number. Note that protons also have a mass of 1 AMU. But if I give chlorine another proton, it's not chlorine anymore. It's now argon. Or if I take a proton away from chlorine, it's not chlorine anymore, it's sulfur. I should also note, practically speaking, you can't just take protons away from things. You can split atoms, and maybe you'll get lucky and you can just split off one, but it doesn't usually work that way. So you can't change the number of protons. So to change the mass number, you can only change the number of neutrons, and this is what isotopes are. And if you look at the periodic table, what you find is that there is this number underneath each atom. Every single atom has that. And if we look at our key, this is the average atomic mass. So when you look at this, it's 35.45. So if you look at this one, this is chlorine 35, and this is chlorine 37. Well, how do they have a mass of 35.45? It's because this is what's called a weighted average. And a weighted average is something that you as students are very familiar with. If you take a test, right, and your 4-hour exams are worth whatever, 40% of your grade, and your final exam is worth 20% of your grade, then you would multiply the average score on the hour exams times 0.4, add it to the average score on the final exam times 0.2, and then whatever rest of the points are, and you have a weighted average because the final exam doesn't count the same as a regular exam. Well, it's the same thing here. We have a weighted average. If in nature there's more chlorine 35, that's going to contribute more towards the average atomic mass. And if there's less chlorine 37, that's going to contribute less to the average atomic mass. So if we look here at this example, which I'm getting ready, we basically have the same thing, just written out typed out. That's what I should say. So this says, naturally occurring chlorine, or Cl, is 75.78% Cl35, which has an exact mass of 34.969 AMU. and it's 24.22% Cl37, which has an exact mass of 36.9966 AMU. I should note that over here, we kind of round these to the nearest whole number, and they're not perfect because this is based on carbon-12, and more sophisticatedly, it's based on the fact that to jam a bunch of protons together takes energy, and that energy comes at the expense of mass. So you lose a little bit, as opposed to if you just added up the actual masses of protons and neutrons, they would be slightly higher. But it takes a tremendous amount of energy to jam those positively charged particles together, so therefore you lose a little bit. That's not super important to our discussion. So we have this naturally occurring chlorine, which is 75.78% Cl35 and 24.22% this. Cl37 with this mass. And we want to take a weighted average. Well, a weighted average, okay, or average mass is equal to the mass of the isotope times the percent of the isotope. And I should probably put a 1 here. Plus the mass of the isotope 2 times the percent of isotope 2. And if you had more, you just add them all in, and some of them do have more. So in this case, we want the mass of isotope 1, which is 34.969 AMU, times the percentage as a number, 0.7578, plus the other isotope, 39.966, times the percentage as a number, not as a percentage, divided by 100, 0.2422. We want to multiply, and these multiply these, then add them together. And what you end up with is 35.45 AMU when you add those together. And this is a weighted average just like you'd take for an exam. Our exam's 40%, so your average times 0.4. Final exam 20%, and that's not the grading scale for this course, I should mention. So you take your final exam score times 0.2, add them together, and add in everything else in the course, and that's how you find your average. You do the exact same thing. What's important to note here is this is where these numbers come from. But if we look back on the periodic table, we find that the average atomic mass is 35.45. For fluorine, it's 19.00. For oxygen, 16.00. For nitrogen, 14.01. This math is where these numbers come from. So in this section of the course, you may be asked to solve problems like this. But more generally speaking, if you want the average atomic mass of something, you don't do math like this. You simply look at your periodic table for the very simple reason that somebody already did that math for you. So you would not be required to do that math. So it is not a coincidence that the average atomic mass that we got on our question was 35.45, and the actual average atomic mass of chlorine was 35.45. So in this section, what we covered was subatomic particles. We learned that protons define the element, and that each element, like helium, has 2 protons, oxygen has 8, and sulfur has 16. We looked at element nomenclature, and we learned that, one second here. We learned that there are several pieces of information, such as the mass number, the atomic number, and the charge. We learned how to figure out how many protons, neutrons, and electrons are in atoms and ions. And then finally, we learned how to calculate the average atomic mass by taking a weighted average of the naturally occurring isotopes times the percentage of each isotope and adding it to the weight and percentage of every other isotope of that particular element. Finally, and I should have mentioned this first, we learned what isotopes are. And isotopes are the same element with a different mass number or a different number of neutrons. These concepts are extremely important to chemistry and will certainly be on your exam.